name is Milan Rollo. I'm from ATT Technologies, and we are currently involved in Imafusa and RefMap projects. But today I will talk about the outcomes of the simulations that we perform for the Imafusa, mainly how we are simulating impact of drone traffic on the public acceptance in large-scale scenarios. What I will be talking about is why we are using the simulation, large-scale simulation, what we need. We touched the issue of available data sources, so how we construct the environment to be realistic. I will briefly talk about the indicators that we are simulating, because within the Imafusa project, hundreds of metrics and indicators were highlighted, but we are only simulating a limited data set that we focused on within the project. I will describe the simulation scenario and briefly present some of the outcomes. You can find much more in the deliverable of the project that we have submitted recently, and it should be available publicly in a few days. So, why we are using large-scale simulations? In the company, we have developed Agentfly Simulator, which is a large-scale, fast-time, agent-based simulation. We are using detailed 3D models of the environment. We are working with the airspace structure definitions, air traffic generators. We are capable of simulating drone traffic, general aviation, and commercial aviation. And we have a lot of data processing, data logging tools. And as a part of the Imafusa project, we took the existing simulation framework. So not everything was done within the project. We are working on the simulator for almost 20 years. And we extended the simulation framework to be able to calculate and log some physical variables that are required for the evaluation of the public acceptance impact. We focused on the noise, visual pollution, and safety perception. All these algorithms were developed by partners in the project in separate work packages. We took the input from them, integrated everything together into the simulation framework, and ran several simulation studies. We also required to have some data loaders for third-party data, like population density maps or ambient noise information, and we are using this to somehow balance the trade-off between the overall capacity of the airspace and the impact of the drone traffic on the public, because we can squeeze thousands of drones simultaneously into the airspace, but there is some cap when you will have a demonstration outside of the major hall and they will say this is enough, we don't want more drones. So we are somehow trying to find the balance between these. And we are later running the simulation on a city scale level with thousands of aircraft operating. So the environment that we are using is using the geospatial data. We are using the detailed terrain model and buildings obstacles from OpenStreetMaps or other data sources like you already saw, for example, for the CFD simulations, the data about the buildings from the TU Delft. We are working with the airspace structure, so we can simulate terminal maneuvering areas, or we can define no-fly zones arbitrarily that can be later done on municipality levels. And for example, you will say, okay, there is going to be some huge sport event or concert somewhere in the city, and we are declaring temporary no-fly zones here from the level of the municipality. This is something that is, the process is not standardized yet on the EU level, but this is something that probably the municipalities will later have such possibilities to do. And we also are using some data related to the metrics that we are calculating, population density maps, urban area classification maps, so we can work with areas that are defined as quiet zones, parks, hospitals, or industrial areas. This is something that we can take into account as well. And we work with the background noise maps. To simulate the air traffic, there is an issue that there is no sufficient drone traffic database available. Fatima was talking about commercial air traffic and DDR2 dataset. This is something very well defined. The commercial air traffic developed for hundreds of years. We have all the data available for what the traffic for one particular day over the European Union looks like. But if you want to do something similar for drones, you will have like 10 flights for the city currently. So this is not sufficient. For this purpose, we are building artificial air traffic generators. When we say, okay, we will have some portion of traffic delivering the goods between the hospitals, from warehouse to end user customers, warehouse to warehouse delivery, survey services, hobby flights, and so on. And we can like somehow tune the parameters and run the traffic and scale the traffic up. So we are creating realistic drone traffic, which is not existing today. For geospatial models, as I already mentioned, we are working with full 3D model of the environment. For terrain, we are using SRTM dataset, which gives us the information about the terrain height. And on the top of the terrain, we are putting buildings. For general, we can work with OpenStreetMaps. This will give you these ugly boxes. Or you can work with more defined models, which is the information, for example, from TU Delft. And you can see that the buildings here have more like fine defined structures. The difference between these two in terms of the mode indicators that we are calculating is not significant, but it's significant, for example, for the CFD simulations, because the turbulences here will be different than on the simplified models. We started to work with, I will probably need somehow to adjust. Okay, it's a PDF, it's not in a full screen mode. Okay, we will go this way. We said, okay, we want to simulate how the drone traffic affects the general population in a city. For this, we said, okay, we need probably to know what are the populated areas and how to work with them. And we didn't know how to tackle, and we decided that we don't want to do this from like a statistical point of view, so that we say we have average 50 people per square kilometer in this area. What we did is that we took population density map. We used Facebook data for good data set. There are other georeference open data sets as well, but we found this quite reliable for the Prague. They are using a combination of information from the mobile operators so that they know where the people with cell phones are moving during the day. So we had like a city limits with the hotspots population density, and we got the information about the total population in Prague, which is 1.3 million of people. So we said, okay, now let's do calculation and place individual people into the city. So we placed, based on the distribution, we placed 1.3 million people to the city. Next step is that we said, okay, but there are buildings, but we have them. We know the information about the buildings. We also know the information about the floor, the number of floors in the city, in individual buildings. So we said, okay, probably more people will be in a 10 stories tall building than next on the ground level. So we like moved more people into the high story buildings, and this is the outcome. So we like have the information about the people that are outside of the buildings, so that they will be affected by the drone traffic. Because what we assume is if you are inside the building, nothing will hit you. You will maybe not see the drones. You will not be affected by the noise, unless you are relaxing on the balcony, having a cigar, but we don't consider this. So we have individual people in the city. Next data set that we are using is an ambient noise map. Again, we got the information from the Prague City Open Data Portal. We have ambient noise maps for daytime and nighttime operation. And for the drones, we are currently using simplified drone noise model, 1/3 octave band, spectrum propagation. Here is like an example how it looks like. So we are able to calculate how the spectrum, how the noise is being propagated through the environment, and what is the impact on the ground. So as the drone flies, we are calculating how far from the drone, what will be the acoustic pressure level on the ground. Next step is to say, okay, so we know the acoustic pressure as a source, we are calculating. Second, we are calculating the propagation. Third, we are calculating the annoyance on the ground. This is for the noise. Second metric that we are calculating is visual perception. When the drone is flying, And visual perception is used for two metrics, visual pollution and safety perception. Visual pollution takes into account how many drones you can see at the moment and how far they are. Safety perception takes into account how far the drone is from you, what is the relative speed of the drone crossing you, how far the drone is from the bystander, because as you see that the drone is flying over a group of people, you will get a little bit nervous what will happen if the drone will fall down. And the third part that makes you nervous is if the drone will hit a building or not. So we are calculating distances from the observer itself, calculating distances from the nearest bystander, and calculating distances from the, you can see that the nearest bystander from this drone is right down below, and this is the nearest building. So this is what we do each second for all the drones, for all the people. These are the metrics that we are calculating, and these are physical values. We are flying the drone, and we are calculating all these variables. What we do next is that we can start to scale up the traffic or scale up the calculation for the number of people on the ground. So here is like here is an example of what we are calculating. This is again the single flight of a drone, and here you can see these are the areas where the perceived noise from the drone on the ground is higher than the ambient sound level. So we can say, okay, here you can hear the drone actually. And this is how it looks like for the safety perception. The safety perception metric combines together how close the drone is from you, how close the drone is from the bystander, and how close the drone is from the building. And here in this scenario, you can see medical drone that will be landing here. What you can see that if the drone will be getting closer, and we have individual people here on the ground. These are these small dots here, everywhere. And if the observers are somewhere here behind the buildings, they cannot see the drone landing. So they don't see that they are getting closer to the bystanders and closer to them itself. So here we are like nicely visualizing that if you don't see it, it doesn't bother you that much. So this is the outcome for the safety perception. I don't have the explanation of the visual pollution, but I will have the graphics later. And now we scale up. This was for like a single drone operation, and now we want to run 80 drones up to 1,000 drones over the city. So what we defined is that we took the Prague city, we defined several no-flight zones, we can turn them on and off, and we have points of interest. So this is the definition of the environment, and we start to generate the traffic. We generate deliveries from warehouses, medical deliveries, cargo flights, and with some rates. And what is important to mention that the safety ranges between the drones as we generate them is 80 meters. This is important because, for example, this will give you the information about how many drones you will see at the same moment for the visual annoyance. If we will reduce this distance, the drones will be more dense and the visual annoyance will increase, for example. And currently we are only simulating the constant cruise speed 15 meters per second because this is the speed for which we have the 1/3 octave bait noise characteristics. Yeah. And another important fact is that we are flying the drones at one flight level at 310 meters AMSL. If we can switch multiple layers, the traffic will double, triple, and so on. So here is a LA Max heat map, which is acoustic pressure, scenario with no flight zones, scenario with flight zones. So here, for example, you can see that we have no flight zones, and the maximum perceived acoustic pressure level will be lower. If we will turn them off, it's basically changing, and we are getting the outcomes that can be later evaluated. Here is the change in annoyance, and you can see that we are like overlaying this map with the ambient noise. So here will be the areas when the ambient noise actually will get higher. Here are areas where highly annoyed people will increase. The metric works in such a way that if your ambient sound level is quite high and you will add more, you will probably get more annoyed. So we are saying, okay, we are increasing already high noise levels and we are getting people more and more annoyed. Here is scenario 80 drones versus 400 drones. So you can see that as the drones will be more and more dense, the maximum pressure level is increasing and the people will perceive higher levels of noise. Visual annoyance maps, you can again see it's like mostly nothing, but in the center it's getting more intense. It's a scenario for 80 drones versus 1600. Safety perception heat map, 80 drones versus 1600. And we are getting to conclusion. We have quite a powerful simulation framework right now, where we are capable of simulating the air traffic and measure various metrics. And this can be used to support airspace capacity assessment studies versus the impact on the public population. And you, as municipality stakeholder, can perform some trade-off analysis. We do not give absolute numbers. We will not say 1,525 flights is enough, because it depends on the configuration of the airspace, locations of the vertiports, and so on. But we can roughly give you numbers about how many people will be highly annoyed in such a scenario. And then it's a decision of the local decision makers if such a number of people that are highly annoyed is enough, or if the benefit from the operational costs or income, increase of the business is justifiable. So we don't give absolute numbers, but we can give guidelines. And there is a lot of future works, because we achieved technology readiness level 1 or 2 outcome. And the 4 most important are related to the metrics and how we calculate them. The indicators will change for higher traffic volumes, because the studies that were done in the IMAFOSA project were using virtual reality. Students or other participants were given VR glasses. There was a 3D environment defined, and some drone traffic was flying. But we don't know what will happen if we will increase the traffic even more, if we will mix multiple events, if the drones will be flying in front and behind and so on. So we don't have all the numbers that we need for higher volumes of traffic. We don't know how to merge various metrics and indicators together. What will happen if we will combine the visual pollution with the noise and safety together? Because highly dangerous event will probably annoy you more than constant noise buzzing. We don't know how to combine the indicators together into one number, so that we will be able to compare 2 scenarios. If we will have one scenario when the drones are flying through unorganized traffic, and second scenario when we will have corridors, we don't know how to compare them together, because we don't have a unified number. For this, we need to aggregate the indicators over an area with multiple observers. Currently, we don't know if 50 people perceiving one event will have total higher annoyance than if the people will be scattered somewhere and will get multiple events at the same time. And the last is we don't know how the indicators will sum up over time. If we will have a constant flow of drones, one drone each 5 minutes all day, if in total you will get more annoyed, or compared to 2 more noisy drones each 30 minutes. What will happen in the long term? So this long-term study of impact on people is unknown as well. And again, we will need to measure and have additional data sets, more drone noise models, higher fidelity 3D models, and what we currently don't consider in the simulation framework is the wind and the Doppler effect, because the wind will highly affect the spread of the noise through the environment, and also the Doppler effect will play a crucial role. If the drone is flying, you can see that the pitch is getting louder, and it's like with a train or car. So this is how where we are so far.